less than 45 concentration. And in less than 45, oopsies, in less than 45 concentration, we will learn how concentration affects chemical reactions. So we'll learn how if you change the concentration of the chemical reaction, it will change its rate. So really it should be chemical reactions rate. How does changing the chemical reaction affect the rate? So that's what we're really going to explore. And so let's go through how it works. Before we do that, let's talk about what we did last time. So last time I had you guys, we talked about two things. We talked about temperature, and we talked about temperature, and we talked about surface area. We said that in order for a reaction to go, you need to have energy and you need to have correct orientation. Now, the main way that we make sure that we've got enough energy and we've got enough correct orientation is by just giving more collisions. More collisions means more chance of correct orientation, so correct energy. In other words, if you play the lottery once, you probably won't win. If you buy 1 million lottery tickets, you probably win something. Okay. If you want to try and get a basketball into a basketball loop, if you throw it once, you probably won't get it in. If you throw it 100 times, you probably get it in at least once. So that's the main thing. Oh, coffee. Thank you. Guys, this is why you should be nice to your partner, because they'll bring you coffee if you're lucky. I appreciate it. Yeah, it's good. It's Starbucks, so it's not that great. But yeah, anyway, let's move on. So, what else? So once we did that, we talked about, well, what's the first way to increase reaction rate? That's the temperature. In a hot sort of place, those particles are moving around super quick. But in a cold environment, they move around very slowly. Now, the question is, increasing the temperature speeds up the rate for two ways. One, the particles have a greater energy. So they're more likely to break the bonds because they're moving around a lot faster. So when they smack into each other, they smack into each other with more energy. But also, because they're moving around so much, they're more likely to collide. If you've got lots and lots of people moving very, very quickly, you're more likely to bump into someone because they're just moving around so much. So that's why temperature is a really good way to speed up the reaction. And that's why when you want your bread to rise, you put it in the oven because it makes it hot and that chemical reaction happens faster. And yeah, so that's why temperature is a great way to speed up chemical reactions. Surface area, well, there's only 12 places to react in this cube, but if I start breaking it up, I can increase it to 24, and then I can increase that number to 36. There is now 3 times as many places. Suddenly this middle one can be accessed by everything. So surface area, by breaking the surface area, you provide more reactants for the chemical to react with. And that's why when you burn firewood, you would use kindling, you would use tinder first because it's got such a high surface area, and then you would move up to the larger sticks afterwards. I probably should have put an example in there for temperature, but that's all right. I couldn't think of a good example for concentration, so I feel like a bit of an idiot. But I think I always like to start with concentration first. For some reason, the style of the textbook haven't, but I'm like, whatever, we'll talk about it now. Concentration, in my opinion, is the easiest one to explain. Firstly, what is concentration? This is something you should know because we talked about it in year 7. You talked about it probably in year 9, but if you've forgotten it, let's do a quick recap. Concentration is the amount of dissolved substance in a liquid. It doesn't even have to be a liquid. It can be the amount of dissolved substance in air. So if you could have concentration of carbon dioxide in cities is higher than in rural area, but whatever, it doesn't matter. Let's just stick to what we know. A high concentration means lots of substance dissolved. So let's go look at this one on the right. This one on the right here has got lots of cordial dissolved. It is a really dark because it's got so much of that dissolved in there. And so therefore we say it's concentrated. Whereas if you have a low concentration, we would say that is dilute. Dilute has barely any substance in there. And that means it's got barely any reactants in there. If you've got a dilute acid, that's not going to be nearly as dangerous as having a concentrated acid. The concentrated acid might burn your hands, but whereas a weak one won't. There was a lot of I'll give you guys a second to copy this down. While you do that, I'm going to ramble over here. There was a big thing when the coronavirus started because they were talking a lot about alcohol and what type of alcohol can kill the coronavirus. And they said, well, it has to be greater than, I think it was like it has to be greater than 70% alcohol. So that means that 70% of it was alcohol, 30% of it was water. I was like, okay, cool. But what some people were doing was what they would do is they go, oh, I'm going to be smart. I'm going to be big brain here. And they thought, I'm going to buy 100% alcohol, which you can buy. That's what essentially is in alcohol wise. And what they thought is they'll do is that I'm going to add aloe vera. And aloe vera, if you don't know what aloe vera is, it's a nice sort of hand sort of like moisturizing kind of thing. So they thought they'd add aloe vera, maybe something that smells nice, like some flavoring or whatever. And I thought, well, we're going to add that. And then the problem is they thought, well, I started with 100% alcohol, so at the end I should have 100% alcohol. And they were completely wrong. Because if you add aloe vera, that's like adding water. If you add water to that, you'll drop the concentration. And so what happened is people drop the concentrations down to like about 50%. And it's like at 50%, you're not even killing the virus anymore, because remember, it has to be more than 70. So 50% alcohol, it's like it's no longer effective. So sure, great. Now you've got this liquid that smells nice and it's got aloe vera in it, so it feels nice in your hands, but it's no longer killing the virus, so it's completely useless. And that's why concentration is important. Understanding that if you add water to something, you will dilute it. And it doesn't have to even be water. It can be things that's like, oh, I'm adding aloe vera. It's like, yeah, but aloe vera is got water. It's going to dilute it. You might think, oh, but no, it's not. You might go, oh, I'm going to add, all right, fine, I won't add aloe vera. Then I'll add something like, I don't know, I'll add something like, we'll go with sunflower, we'll go with lavender extract. It's like, well, lavender extract has got oil in it, so that's going to dilute your alcohol. It's like whenever you add something, you're going to dilute it. Anyway, but that's, that's from a chemistry perspective. And if you guys do year 11 and 12 chem, if you do choose to do that, you guys can actually learn how these numbers work, so you can actually see how badly they stuffed up. But that's just in general. If you're not going to do year 11 and 12 chemistry, then that's just what it means. Let's talk about the next idea here. So concentration, in my opinion, is the easiest one to explain how the rate of reaction works. High concentration means more reactants. More reactants means more collisions, so a greater chance of making product and a faster rate. It's like, in my opinion, it's the easiest of them all, because although temperature and surface area are confusing, a little bit difficult, concentration is the easiest. If there's more stuff, it'll go faster. It's the same sort of thing as whenever you will do a chemical reaction as a demonstration for students, and they're like, oh, sir, add more. And you're like, well, if I add more, the reaction's going to go bigger. That's exactly what it is. If you want to get a Mentos reaction going if you're going to get a Mentos reaction going with, actually, I better not talk about the Mentos reaction, because that's actually surface area. Ooh, good point. Might talk about that at the end. But yeah, if you want to get reaction going, just add more concentration. So the top one, look, there was like 3 or 4 collisions there, whereas in this bottom one, sorry, I haven't got this to work properly, but yeah, this bottom one, because there's so few, chemicals, because it's so dilute, they're not going to react. So because they're not going to react, because they're just not going to collide enough. In this one, there are so many particles, you can't even move like 1 centimeter without banging into something. But in this one, you could travel like 10, 15 centimeters before you meet another particle. That's why more higher concentration means more reactants, because there are more reactants here, which mean more reactants mean more collisions, so there's a greater chance of making the rate go. I'm going to keep this up for another 30 seconds and then I'm going to change the slide. What time is it? Okay. Now there is one additional way that you can sort of cheat the system, and you can change the reaction. Now, concentration, if you don't know, is the amount of stuff in a certain amount of liquid. It's like density. So there is a cheating way that you can actually increase the rate without adding more substance. Now, it's not really cheating. I just like using the word cheating because it kind of gets students like, oh, I'm breaking the rules. You're not really. If you've got this bottom one, you can make this bottom one react faster by doing this. By changing the size of the reaction vessel. If you squash that reaction vessel up, just looking at this bottom right hand example here, those chemicals, even if there's still the same number of them, because they're all squashed up, they're more likely to react. They're more likely to crash into each other. So another way of increasing the concentration is by changing the volume. This might mean, and this of course, changing the volume can be different things. If you've got a high pressure vessel, you might squash that vessel. You've got like if it's in a syringe, you might push it so that air in the syringe is more compressed. But of course, if you've got liquid, you could actually just remove some of the water. You could actually evaporate the water. If you evaporate the water, then you've got a higher concentration because there's less water in there and there's less space for it to react. You can think about it the same way. So then that will work. It's just another way. But in both cases, you're still just increasing the concentration. You're still increasing the amount of reactant per centimeter squared or whatever. So, yeah. That's it. Without further ado, what we're going to do now is I'm going to pop open Style. I'm going to show you one of the animations in Style, and then I'm going to give you guys the rest of the time to work on it. So let me just open Style. What we're going to do is we're going to set for this chemical reaction, we're going to set this concentration is low, this one is medium, and this one is high. You can see, right, there's only like about like 10 reactants here. Whereas there's like a lot more here, and there's even more. The other problem with concentration is if there's not enough reactants, you're not even going to, it's not only is the reaction going to be slow, but you're not even going to see much product. So let's watch. Okay. In the fast one, in the concentrated one, look at that. It's almost all gone in less than 10 seconds, and it's gone. That's it. It's all gone. Whereas in the concentrated one, whereas in this half concentrated one, you got a lot of it still there, but some of it's going. Whereas in the dilute one, you got nothing happening. Like everything's reacted already. So let's stop it here. Let's go have a look here. We can see with the concentrated one, that reaction takes off super quickly. Whereas the trial 2, the medium concentrated one, takes a little bit of time, but then eventually it reaches the end. Whereas the dilute one just doesn't, like, takes a long time to get started and then doesn't even have enough reactants to make the whole thing work. So that's really important discovery there. Is like, yeah. So you will see here in this, and the reason it flattens out for this one here is because everything's reacted. So it's reacted. There's nothing left to react. 100% of it's being reacted. Whereas in this one, there was only 10% of it reacted because we ran out of reactant. In this one, we probably could leave it a little bit longer. You can see there's a couple of little dots here that could go into react. But at the moment, like, I'm pretty happy with where we are there for that. So then that should help you answer these questions here. It's like, okay, which concentration setting produced the fastest reaction? Explain your results using collision theory. By the way, collision theory is like, okay, they are more likely to get a collision in this reaction because why? Explain it. Is the reaction in is the reaction in the interactive precedes the concentration of what happens to yellow particles? So the yellow particles decrease, there's less of them. How does the answer to the previous question explain the typical curve? And so you want to try and talk about that. And then there's some extra bits here, and then that's about the end of it. So I'm going to let you guys now work on that.